Okay, guys, so we will start. Just a quick confirmation. I am audible and you are able to see my screen.
Yes, Abdul.
Okay, great. Thank you. So, guys, last to last class, we started the micropartition data structure of Snowflake. And now we are aware that logically, when we fire any query on the Snowflake data warehouse through the web UI, we know that we get a representation of data in the form of rows and columns, but that is a logical representation, and it's also a representation done in relational database management systems, right? Like Oracle, Teradata, SQL Server. These are all RDBMS systems, relational database systems. So this relational database systems, relation is nothing but a row, right? If you I'm sure you must have read in your engineering the EF chord rules, the theory of EF chord. If you have interest, you can go revisit it. But in a nutshell, relation is nothing but a row, right? And opposed to that, then there are NoSQL databases, which is MongoDB and Cassandra and all, and they are normally document-based, schema-less kind of a representation they have in the data. So this is an RDBMS representation that we see on the front end when we fire a query. But behind the scenes, it is, and we also know though, that cloud data warehouse, Snowflake data warehouse is hosted on cloud. It uses the cloud services behind the scenes. And since we are focusing on AWS, it is S3 behind the scenes. This all data goes and gets stored in S3. And there it is stored in the form of small blocks of partitions. Okay, which is why they are small blocks and they're contiguous, locations, one by side each other to each other, and they are very small. They range from the size of 50 MB to 500 MB, which is why it is called as micropartition also, right? So it is the physical structure behind the scenes is micropartition. It is divided into small blocks, you can say, or partitions, you can say, and the other important point is they are columnar oriented. They are stored in a columnar oriented fashion. So if you see here, this is the logical representation. So this has column type, name, country, date. If we fire a query on this table, we'll get it in the form of rows and columns like this, right? Type, name, and country and date. But behind the scenes, the physical structure in the S3, Snowflake basically converts. Whenever the data goes and gets stored in S3, the Snowflake converts it into micropartitions. Okay, and it also is compressed. Snowflake compresses it as per its proprietary algorithm. Okay, and so this is basically compressed as well as divided into micropartitions. And second important point is it is columnar oriented, where the columns are stored together. Okay, so type, all the type values, so this is your type column here. So whatever values are there in the type, they will be stored together, right? Up to that limit of partition. So the size limit is 50 MB to 500 MB. So if there's no space within that range, the other call values will go to the other partition. So if you see carefully here in this case, and how the partitions are created, it is as per the order the data comes in. So whatever row comes in first, second, third, fourth, that way it will go into those micro partitions. Okay. And later on, we will see how we can, have our custom-based partitions. How can we do that as a developer or as an architect? That is also possible. But if we don't specify anything, then Snowflake creates the partitions data in a fashion they are received, in the order they are received. Okay, so if you see here, this how many rows are stored. If you see one, so also each micro partition has a header which stores the metadata of the data that is residing within that micro partition. So what are the various metadata it stores is the row count. Okay, sorry, this is the metadata cache here. So it stores a range of values for each of the columns in the micropartition, the number of distinct values, and some additional properties which it requires for effective query processing and optimization. So if you see here, it says the micropartition one here has stored rows from 1 to 6, right? So it is this 1, 2, 3, 4, 5, 6. Till here, it is in micropartition 1. And so on. From 7 to 12, it is in this. So colors, if you see the colors are representing them. This from here to here, that is 13 to 18, they are stored here. And from this last one, from 19 to 24, they are stored in the micropartition 4. So basically, it is as per the order it is received. Okay. So if you see here, this is first row is 2A, UK, and 111 by 2. So this is first, this type. So as I said, columns are all stored together. So if you see this type here, this is 2, this is A, and this is UK, and this is 11 by 2. The date, this is one row, right? This is one row. The second row is here, 4C, SP 11 by 2, and 4C, SP 11 by 2, like this. Okay, so Snowflake tries to ensure that that same row, that particular row resides in the same micropartition. Okay, although they are distributed column wise, but it tries to make sure that that particular whole row, it doesn't spill out to other micropartition. It can in some cases, but it tries to make sure that that whole row resides in one micropartition, so they don't have to scan other micropartitions also. Okay, so that is what Snowflake does behind the scenes. We are not bothered about it. This is called as horizontal partitioning also, guys. Okay, because we are storing it in the one partition only, that whole row. So it is a term. It is called as horizontal partitioning. But when the rows spill to different micro partitions, that is called as vertical partitioning. Okay, so in this case, it is horizontal partitioning here. Okay, so any doubts here before I continue further? This was just a recap of what we did in the last sessions.
No doubts.
Okay, thank you. So let's move further. I'm going to do a demo also. Okay, so let's see what query processing in Snowflake, how it is done when you have micro partitions. So say this is the table. We are continuing with this table example only. Okay, and this is taken from the documentation itself, the Snowflake documentation. And yeah, so whenever you fire a query, select type. In this case, select type, name, country from employee, where date is 11 by 2. So as you all know, first the query goes to the query process, the cloud service layer. It does all the authentication, compilation of query, authorization of the user session, then optimization plan, etc. Then it sends the query over to, before sending, it also does the reading of the header files, or the header files basically reside in each micro partition. Correct? I increase it. So each micro partition has its own header, which has those metadata information, right? The what we call the range of the values, the distinct values of the columns. Based on that, it decides on my where condition whether I need to scan that partition or not. Okay, and that is called as partition pruning, right? And after that, once it has decided, okay, out of 4 partitions, in this case, out of 4 partitions, I need to scan say 3 partitions only. That is the selected partitions, and the pruned ones are which are cancelled out. And that is possible by checking the metadata or the header file of the micro partition, right? So now in this case, it has decided and it has come to know that micro partition 1, 2, and 3, there is where our 11 by 2 related data is there, right? See here, the last partition here, it doesn't have 11 by 2 here. So how did it get that information? By reading the header metadata information from each micro partition. It did not have to go and scan and check, okay, each row, okay, 11 by 2, is it there in this? Is it there in this? It's not, it did not do it like that. Otherwise, it would have been very inefficient, right? So header and metadata is why it's so important, and that's why it's so quick also. I mean, it doesn't take much time to read the header information. So yeah, so where date is 11 by 2, it has come to a conclusion that it is going to scan 3 partitions here. And in this also, what are we asking to give us back? Type, name, and country. So it is just going to give type, name, and country. So these 3 only it's going to, I mean, these 3 blocks in each, all the 3 micro partitions is going to read. It's not going to even bother scanning this last date column part. So that way, columnar, columnar oriented databases are also very efficient. Okay. In some cases, like mostly for the reporting part, they are most efficient, because in reportings, we don't fetch, in our select queries, we don't fetch all the columns, right? We fetch normally some columns, and then we do the reporting on that part. So that is why for the OLAP systems, columnar oriented databases are more preferred, where the reporting is done. But where OLTP is done, where the transactions are being logged in, you normally fill up all the columns in the table. Like 90% of the columns, at least you will fill up. So there, the row-wise oriented column fashion is better. Okay, so it's not that only column oriented is better than row. It's not like that. Each one of them have their own purpose. Next is a column selection. So obviously, depending on what you have selected, it is just going to, read those blocks. And this is not required. Okay. Snowflake loads data into the micro partitions as and when data is inserted into the table, right? That's what I just mentioned, and also in the last class, that as per the data you have inserted, you are inserting one by one the row. That gets inserted into micro partitions as it is, one by one. That is it. There's no other way Snowflake does it. That is the default way Snowflake will load data into micro partitions. Okay, yes, but you can change that, but we'll see later how we can do that. Okay, guys, see now here, I'll just go back to the, I'll go back to this data here. See, let's just focus on the date here, okay, because this has become a natural column to, partition on. See here, so 11 by 2, it is continuously coming up till here, right? It is continuously coming up till here. Then 11 by 3 starts to come. Okay, so all this, the 11 by 2 before 11 by 3 till here, see, it all got stored one by one as it is in the order it came till micro partition 2 here, right? After that, 11 by 3 started from here. Then 11 by 3 kept continuing for 3 rows, and again 11 by 2 started to come. So 11 by 2 went on to third partition. Then again 11 by 3 came, so it also went to third partition, and then 11 by 4 came. After that, 11 by 4 came and 11 by 5 came. So they moved to partition 4. Okay, so when, let me go back to that slide here. So when you don't have the same value of that column in the partition. For example, you have 11 by 2 here also, you have 11 by 2 here also, but you have other values also inside it. So that is called as an overlapping data. So these 2 partitions have overlapping values, or actually all these 3 partitions are having overlap values, but these 2 partitions are not purely having 11 by 2, but they also have other values within them. That is why they have overlapping data, which means they have some other value also apart from 11 by 2. If you consider 11 by 2, okay. So for 11 by 3, you have these 2 overlapping partitions, because you have 11 by 3 in this column, in this micro partition. You have it in this micro partition also, but apart from it, you have more other values, 11 by 2 and 11 by 4. If you talk about 11 by 4 perspective, it doesn't have any overlapping partition. It is just in this partition itself. Correct? So this is what overlapping means.
Abdul, one question.
Yeah.
Let's assume there is a column called vendor code in this table, and for first 6 months, we have some valid vendor codes coming in. So there will be another column vendor code, and all the 3 micro partitions will have some vendor codes.
You're saying one new column. You're saying
new column, yeah, vendor
okay.
code. Let's assume.
Yeah.
So
Yeah.
for from the month of January to June, the vendor code was generated and it was coming correctly. So the business was interested in some kind of analysis or some kind of details on the vendor code, and then they started using it. After June or July, the vendor code was some corrections were to be made. The source system did not send the vendor code. Okay, so but we want that column to be there, but from the ETL or from whatever we are loading from the external system, we are just pushing it as an empty column. Okay. So in that case, so when we are doing this micro partition, how that will be maybe how it will be architected or stored in the micro partition, or how it will be like basically what I wanted to say is after 6 months again we are going to reuse it actually. So we are not going to change the structure, but we are not populating that column for some 6 months of period. So in that place, how the micro partition will behave, or it will be redesigned accordingly inside Snowflake.
Okay. So who is this?
Vinod.
Okay. Okay, Vinod. So what happens is basically the way null values are used in Snowflake is that it is any random value. Okay, so it will as per the order. It will still be a part of row, right? For example,
yes, it will be part of a row.
Right. So let's go to Excel. Okay, just for a minute, and say this is your type column. Okay, this is your say name. This is your UK. This is your date, and this is your null. Correct. So let's say this is for initial 3 months, there is some code coming here for vendor code. And from this point onwards, this from June, right?
Yeah.
Yeah, June. This starts to come as null.
Correct.
Till say another 3-4 months, maybe whatever. And you are recording them as null only.
Correct. Yes.
Right. So, as I said, this is a thumb rule. Snowflake loads data into the micropartition as and when data is inserted into the table. So this will come to whatever micropartition it will come in till whatever 50 to 500 MB size space is there. It will store those this data into those micropartitions, and later on, if the size is not feasible for them to store further data, it will spill to the other micropartition. So there is no special way of handling the null values in the micropartition. Okay. And to answer your other question, you said that later on these will be populated based on
the corrections, whatever corrections they have done. Yeah, from
right. Correct. So I will answer that to you in a moment.
Okay.
Okay. So we are going to come to that point, and for that we need to understand. So basically, what you will be doing is you will be going to update this row. Basically.
Correct. Yes.
Correct. So you are going to do an update operation actually. So wherever it is null, you are going to update it.
Correct.
As per your whatever sequence or whatever your logic is behind that.
Yes,
so I will come to that in some time. Okay, because that point is covered here. I'll come to that. So this overlapping is it? Have you understood this?
Yeah. Yeah. Correct.
Okay. Yeah. So it says single micropartition can hold all the data only if micropartition is between 50 to 500 MB, which means this whole row, right? As I said, if it is possible, firstly, Snowflake will try its maximum best to have one row in the same micropartition, that same row in the same micropartition. But if not, it will spill out. It will spill out to other micropartition. Okay. So yes. So the very first point is each micropartition is immutable. Okay. So you understand the meaning of immutable? Which immutable means you cannot change this micropartition value. For example, if you want to update this, suppose you want to update this null vendor code. Let's talk about this and say this is in micropartition 5, suppose. Okay. And you want to update this row to say, vendor code or say 1, 2, 3 like this, suppose. The micropartitions in Snowflake are immutable. Okay, that is also the property of S3. Basically, we are storing it in S3, right, behind the scenes as far as AWS Snowflake is concerned. So you cannot change S3 files. Okay, that is why this property is also carried forward to Snowflake and it is immutable. You cannot do this. What happens is when you update the column in a micropartition, see what happens. This means if there are updates within a micropartition, a new micropartition is created. This whole micropartition, right? It gets detagged, or you can say in the metadata. Guys, am I audible?
Yes, Abdul.
Okay.
Yes, sir.
Yeah, I got one message. My internet connection is not stable. Okay, anyway. So this metadata in the Snowflake, it says that this micropartition is no more valid data. Okay, it marks it as deleted actually. So update operation in Snowflake is actually delete and insert. Okay, it's not going to go and update on the same row. It's going to delete and it's going to insert a new row. It's basic,
right? So it's absurd.
Yeah. No, I'm not sure whether upsert deletes first and insert. Is it like that? Because upsert is also merged if I'm not mistaken.
I think so. I'm not sure basically.
Because
Okay.
Because what happens is it's important that it gets deleted also.
Okay.
Okay. So because I don't know. I'll check up. Maybe I'll look up what upsert is exactly. But
Okay. Yeah.
there's something called as merge also, right? Where if you find the row, you update it, and if you don't find the row, you insert it. So I think upsert is also that. But here, it's important to note that it gets deleted first and then inserted also. So these two operations happen in case of update in Snowflake because of the property of micropartition being immutable. Immutable means you cannot change it. Okay, which means, has any one of you worked on Python?
No.
No, right? Okay, so see, in Python, I mean, any programming language has so many variables, right? Sorry, data types like in string, list, set, etc. They have so many data types. So in Python, there are certain data types which are immutable. For example, string, right? So for consider there is a variable, and variable is nothing but an address, and addresses are nothing but hexadecimal addresses, right? So let's just for our understanding sake say this is 1, 2, 3, 4, 5, 6, and this is a variable. This is a physical memory address, and say in the program we have called this as say name as a variable, and inside this we have suppose say stored Vinod. Okay, so the value of name is Vinod. That is so in Python strings are immutable. That means these cannot be changed. Okay, this value here, it cannot be changed. It means immutable means that. Okay, str is immutable in Python. But if you go in the program, if you go and say change name to Arumu, so what happens is it doesn't come and write or replace Vinod here. It goes and creates a new variable. it basically points this name, okay? It's to a new physical location, physical address. From here to here, it points to here now, and it's no more tagged to this location. And suppose this is HX, 98765 something, some hexadecimal and some number, and this is now it writes Arumuga here. Okay, so name now, this name variable is now pointing to this new memory location, and whenever you try to print the value of name, it will now give you Arumuga. Okay, it did not replace it directly here. It simply created a new one, and now name is pointing to this location. So this location has no pointer. I mean, this location has no linkage with anyone. And this is called as to free up this memory. So this memory will be occupied, right, by the name of the value of Vinod. So Python has its own automatic garbage collection behind the scenes. So it frees up the memory on its own. We don't have to worry about it like in C++ and all. Okay, so Python does that automatically, but this is what an immutable concept is. Okay, you understood, right, what immutable means now? So here also, similarly, carrying on forward that concept, the micropartition here doesn't get updated. This whole micropartition 5, okay, this MP5, it gets deleted, and it's not a physical delete, guys. It's a metadata delete. Okay? And metadata marks it as delete. Okay? And a new micropartition gets created, say MP6, and here you will have those values. And say whatever, consider them as some other values. Okay. Consider them as some other number. So this becomes now MP6. MP5 is gone now. That is what the property of micropartition is, and sometimes it is asked in certification also whether it is micropartition is mutable or immutable. Okay, so did you understand this? Did it answer your question, the second
Yes.
part?
Yes, sir.
Okay.
Abdul, I have one question, Abdul.
Yeah.
Can you go back to that PPT where you showed me the micro partition example? Yeah.
This one?
Yes. Okay. So in this case, if I'm doing any of the DML operation, my micro partition will be deleted and new one is created. Is correct?
Only for update, not for insert.
Okay. Even for delete. Yes. Also, if I'm deleting any record, also the micro partition will get deleted and new one created, right?
Yes, exactly.
Okay. In this case, if I'm doing any delete or update in the micropartition 2 means my micropartition 2 gets deleted. So the new one created, that will be the micropartition 4. I mean, the max plus 1 will be created, right? Or how it works?
No, not necessary. See, these, if we consider this particular example, there are 4 micropartitions.
Okay.
Correct? And say we updated something in 2. So it will become 5. It will go to it will become micropartition 5.
Yeah, that's what. So max will be the 4. So
okay, max plus 1 you said. Yeah, that's right. Yes.
Okay.
Yes.
Fine. So the new metadata like the distinct value and the range, everything will be created newly for that partition, right?
Yes, exactly. Correct.
Okay. But here if I'm deleting the micro partition 2, the range is here shown like a 7 to 12, right? So the same range will be there in the new partition?
Yeah. So if you have only updated something, it will be same. But if you delete, say, one row, if you delete one row from here, that time it will not be same, right? That time it will be that the range will change.
Correct. So in that case, the following micro partition, everything will be altered then?
Yeah, absolutely.
So all those partition gets deleted and new one created?
No. This if you are deleting, say, this 3 rows in this micro partition 2.
Yeah, I'm deleting only 8th row.
8th row, which is in this one, this micro partition 2. Yeah, so this whole micropartition is marked as deleted. It is not a physical delete. Okay. The metadata here is marked as deleted. Then MP5 will be created, and there the whatever latest data is there, it will be stored there with the metadata also getting changed, of course.
Okay, but I have deleted 8th row, right? So the
Yeah.
rows and the third partition shows a range like a 13 to 18. There won't be any change because of the recent change. I mean, the 8th row got deleted, right?
No, because you have done alterations or changes in this partition, right?
Correct.
So there is no impact on other partitions.
Okay, because of the changes in the row, the range will not changes for the other partition, right?
No, no, no.
Okay, okay, fine.
Okay. And see, this property is immutable. As I said, micropartition is immutable, right? So if you change here, you cannot, I mean, it is anyway not possible to get changes done on the other micropartitions because once they have been created, they are immutable.
Okay, fine, fine.
Okay. And all these things is, being done behind the scenes. You don't need to even worry at all, like whether, Snowflake has created the metadata or not, what it has done. It's all automatic. So that management is very minimal in Snowflake. You don't have to worry about it at all. So it's the duty of cloud service layer to ensure all the metadatas are proper in each micropartition and the pruning, etc. It's done properly behind the scenes.
Okay. One more question, Abdul, but I'm not sure
Yeah.
whether this is the right time. So,
No, ask.
you talked about spilling rows to the other partition, right? If I'm updating 2 column for the same row which spilled between partition 2 and 3, in that case, both will be deleted and new one
Yeah.
created.
Yes, definitely.
Uh-huh. Okay. Okay, fine.
Yeah. Okay, overlap, I just told you guys. Yeah. So see, we just saw what micropartition property is, that is immutable, and Snowflake uses this immutable feature. Okay, for so many other features it has. It has got zero copy cloning. It has got time travel, fail safe, data sharing. We'll be going to study all these topics in detail. But why these features are available for Snowflake? Why they are able to leverage? So basically, they leverage this S3 property that it is immutable, and which is why the micropartition is also immutable. That is because of that these features are also possible to be offered by Snowflake. This is the reason. Okay, the zero copy clone, time travel, fail safe, data sharing, and all that, which we'll see later on. It is because of this property. Micro-partitioning is automatically performed on all Snowflake tables. Tables are transparently partitioned using the ordering of the data as it is inserted and loaded. That's what we have seen. As the data is inserted, partitions will be created as per that order. Okay. Snowflake will do nothing, no other, brainstorming on looking at analyzing the data. Okay, this is an efficient way to do it. Nothing doing. It will simply, okay, this row has come first, go to partition 1, this row has come 10th, go to partition 2, and so on. All DML operations, delete, update, merge, take advantage of the underlying micropartition metadata to facilitate and simplify table maintenance. For example, some operations such as deleting all rows from a table are metadata only operations. So suppose we are going to delete, say, the whole row in micropartition 2. So it doesn't have to go and physically delete all this. All it does is go and tell the metadata header that this partition is no more required. So isn't it a faster process? Instead of going so many, if suppose this has got hundred thousands of data inside this micropartition, it doesn't have to go and free up the memory for all of them. It simply has to go and say, okay, this partition is no more available now. So when you query, just kick this partition out. That's it. So that's why it takes the advantage of that. Okay. So before going to the benefits, let's look at a few things here. So see, guys, I'll create one table, okay? I'll create this table here. And I will not do the clustering. I'm just creating a simple table, that's all. Okay, I created this table, and after this, I will insert some values, some rows also. So see, I am inserting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rows. I have this, so I have C1 and C2 columns. I have inserted 12 rows. And if I want to see the clustering information, I can always go and do show tables. If you say show tables, it will give you information of all the tables. Like if I only enter this, it will give me table information of all the tables. If I want a specific one, I can say like and give the table name. So this is, it will give you certain information here. So see, it says clustering is off. Automatic clustering is off. Okay. And there's no clustering. Okay, so I have not come to clustering yet, so just forget this right now. I'll come to that in some time. So what has Snowflake done behind the scenes? When I inserted these 12 rows, what has it done actually? See, it created how many micro partitions? 3. This is a hypothetical example, guys. Okay, it has created 3 micro partitions. That is 4 rows per micro partition, and it took it as the order, or as in the order. Okay, so see, micro partition 1, it took 1 1 3 5 5 9 6 12, right? 1 1 3 5 5 9 6 12, this way as it is. And in micro partition 2, it took from 4 7 to 3 6, that is 4 7 to 3 6. And the other one, it took, sorry, it took till 5 10, sorry, 6 11, it took till 6 11. Then the rest of it from 2 4 to 4 8, it took it put it in the third part, third micro partition. So if you see, micro partition 1 looks like this. So as you know, it is a columnar oriented structure behind the scenes. So all the column values will be collected together or stored together, and other column will be stored together. So in micro partition 1, is columns 1 3 5 6, is 1 3 5 and 6, they got stored together, and 1 5 9 12, they got stored together in the same micro partition. Same is the case for micro partition 2 and micro partition 3. Correct? This is what we just learned, right? Okay. Now we'll come to the benefits later. Let's talk about data clustering. Okay. We now till now have.
Abdul, sorry to disturb you.
Yeah.
One question.
Yeah.
Usually the partition will be between 50 to 500 MB, right? Then
Yes.
only it will create the second partition. But in this case, you just inserted only 5 rows, right? The memory went beyond 500 MB or what?
No, this is just a hypothetical example.
Okay.
Yeah. I just mentioned, right? Let's consider that it's a hypothetical example. Let's say it is trying to create 3 micro partitions with 4 rows per micro partition.
Okay, we don't have any control, right? So it just created itself.
Yeah, it created itself behind the scenes. It is just a hypothetical example to show you the concept. Okay, it will definitely have the micro partitions size limited to 50 to 500 MB. This is not definitely that much size, but just for explanation purpose, I am showing you this.
Got it. Okay.
Okay, even this is not 50 to 500 MB, right? This is just for explanation purpose.
Okay.
Yeah, correct. So now this is as per the order which Snowflake has created the micropartitions. Now we go a little further down here somewhere. See, in this case, we have maximum. We said that uh, it stores the metadata and it has got the min and max values of the columns as well. So if you talk about C1 column, so micropartition 1 has minimum as 1, maximum as 6. Correct? So let's stick to micropartition 1 only. That would be enough. So it has 1 max, 1 minimum and 6 as max. Okay. Now suppose we want to customize the micropartitioning arrangement. We don't want Snowflake to do as per the order it is inserted. We want to have our own strategy, and we want to tell Snowflake, we will tell you which column you should create micropartition by. Okay. And that is called as clustering, where you divide the micropartitions based on the clustering key. And clustering key is nothing but the column or the group of column based on which you will create the micropartitions or divide the micropartitions. Okay. I will show that to you also in some time. Let's just read it quickly. Typically, data stored in tables is sorted or ordered along natural dimensions, example, date or geographic regions. So just now in our previous example, the date column was a natural clustering key. Based on this, there was a natural micropartition that was getting created, with that group, with same value groups. Although it is not 100% with that group, it has been divided, but somewhat it has reached that, division using that date column. It was naturally done because of the nature of this dimension column, right? But so the clustering is a key factor in queries because table that is not sorted or is only partially sorted may impact query performance, particularly on large tables. So here, in this case, this is partially sorted, right? 11 by 2 came as a group earlier. Some 6-7 rows came, some 12 rows in the initial, they came all as 11 by 2. So it was all sorted by date. But later on, some other values started to come, and again, the 11 by 2 started to come, and again, so on. So it is partially sorted. So over the time, when data keeps growing, as it becomes larger and larger, and as this group spans, more number of micropartitions, so the more micropartitions you will have to scan, because they are spread across so many other micropartitions, or basically they are not properly grouped together. Correct? They're not properly grouped together. So it is partially sorted. And that is called as clustering. Based on the column it has got divided, it is called as clustering. This is a natural cluster that got created here because of the dimension date. So in Snowflake, as data is inserted into a table, clustering metadata is collected and recorded for each partition created during the process. Snowflake then leverages this clustering information to avoid unnecessary scanning of micropartitions. Snowflake maintains clustering metadata for the micropartitions in the table, including the total number of micropartitions that comprise the table. So this metadata of micropartitions is also with the Snowflake. Okay. So how many total number of micropartitions does this table have? That is also there with the Snowflake. The number of micropartitions containing values that overlap with each other. Right. So this overlap is there here. Right? This overlaps. That metadata is also there with Snowflake. The depth of overlying micropartitions. Okay, so we'll see what the depth of micropartitions is. And this partitions during queries significantly accelerating the performance of queries that reference these columns. Okay, so what is clustering depth? Okay. So as I said, you can, if you don't tell Snowflake about the way you want to cluster or create micro partitions, it will load data into the micro partitions based on the order that it is received. But there is a way, if you say, and that becomes the clustering key, whatever Snowflake decides. But ideally, there's no clustering key if it is storing by itself. But if you say that, okay, I want to, in this case, for example, in this case, you say, I want to cluster by date. Okay. And whatever my data comes, it should be based, micro partitions should be created based on date. Okay. You should bypass your default way of storing data, that is by in the order it comes, not like that, but you have to sort it based on my clustering, my date column, which I'll provide you, and that becomes the clustering key for that table. Okay. So while defining the table, or later on also you can alter the table, you can specify the clustering key to the Snowflake, by which it understands, okay, I have to create micro partitions based on the date. So after, if you say, in this case, if you say, I want it to be done by date, see how it looks. See here. This is the original micro partitions here. Okay. Say this got created. Okay. We did not specify anything as a cluster key. So Snowflake divided the micro partition as the order. So look at this, 11 by 2, 11 by 2 came. It is still there till micro partition 2. And later on 11 by 3 started to come. Then 11 by 2 came again. So it went to micro partition 3. Then 11 by 3 came, and again 11 by 3 came. It went to micro partition 4. Okay. Now I decide, okay, I want it to be created as per my date and as per my type column. So this is the syntax, or this is the command. If you have the knowledge that, okay, I want to do it from the beginning only, you can have this cluster by sentence, or this command created along with the create table itself. But in this case, let's consider we have already loaded the data without specifying our customized clustering key. Okay, so later on we decide that we will alter it, and we'll say that cluster by date and type. Cluster means I want to divide my micro partitions based on date and type. Basically, I want to sort it based on my date and type. So what Snowflake does is it will recluster it. Okay, recluster the micro partitions, and see now all the 11 by 2, and then 11 by 2 also, whatever type are there as 2, 11 by 2 and 2, all are together. 11 by 2 and 3 are all together. 11 by 2 and 4 are all together. 11 by 3, 5, 11 by 3, 1 all together. 11 by 4, 11 by 4 all together. And then 11 by 5, 11 by 5 all together, like this. So already these micro partitions were existing. So see what it did. It created new micro partitions, 5, 6, 7, 8. It did not go and do any updations or rearrangement of it did not do any shuffling between them within these micro partitions. It didn't do that, right? It simply might have marked them as deleted and created altogether new micro partitions based on the cluster by key or clustering key that we supplied to it. Did you understand this?
Yes, Abdul, but if you are doing partition based on the date and type, micro partition 6 should have only 3 in the type, and the date has 11 too. That's fine. Why we have 4 also? That should be moved to a different partition, right?
No, this is because of the size. If it is having space till 50 to 50 MB, it will not let it waste. It will keep that there.
So if that is the case, then here one partition is based only on the date, right? Not on the type. If I have both 3 and 4, right? So because if you look at the Oracle, the partition, if you are doing, then that partition will have only that row, right? Only the date and the type. my question is why this partition have 3 and 4? That is what I'm trying to understand.
Yeah, I understood your question. But what happens is Snowflake says that my partition has to be 50 to 500 MB. So
Correct.
if there is space in there, so it will accommodate the data with it. So if you see here also, in this 11/4 and 11/5 is also there here. Okay, there is no point of creating, I mean, ultimately it's the rule of that, that particular size has to be there. So suppose if this size, if it was say 20 MB for this case, you said that 11/2 should be together and 11 by say 11 and 3 should be together and 11/4 should be moved to other separate partition. That's what you meant, right? So say 11 and 3 have 20 MB of data, and rest of it is empty. It is just consuming 20 MB of data. So Snowflake doesn't do that. Snowflake will not create another and say 11 and 4 consume 20 MB again together. Okay, so it will not create that partition that way because the limit is 50 to 500 MB. It will follow that rule.
Okay, so if I'm not reaching my 500 MB size, if so in that case, if my date has 11.2, 11.3, 11.4, 11.5 accommodated in the same partition, which is micro partition 6, still my query performance will be fast, even if I'm going with the clustering based on the date.
Yes. So now look at this case here. So in this case, let's go to this query here, right? Select name from T1 where type equal to 2 and date equal to 11/2. Okay. Before clustering, it actually had to scan how many partitions? 3, right? This two type 2 is spanning across micro partition 1 and 2 and 3, and this date is also spanning across till this 3 micro partition 3. But after reclustering, it is only micro partition 1 that type 2 and date. So just one micro partition compared to 3 micro partitions. So this scanning is better, right? We are just scanning one micro partition. Rest of them are all pruned.
Okay. This case is fine, but if I'm not reaching 500 MB, all my 11.2, 11.3, 11.4 and 11.5 and all the types are sitting in single partition, in that case also my query will run fast.
Yeah, I mean, in this case, if you want to go for what 11/5 maybe, okay, it has got an overlapping value here, right, with 11/4. So still in that case also just one micro partition you are scanning, right?
No, I'm not talking about this case. So before clustering also, I had only one partition where the date spanning between 11 to 11 to 11.3, 11.4, 11.5 and the type, everything I had in the single partition before cluster as well as after cluster. So because assuming my memory didn't cross 500 MB. Okay. In that case, I had only single partition. Both my before cluster as well as after cluster, will there be any performance improvement because of single partition?
For which case 11/5?
Any date.
Any case,
Because
any case.
all the dates sitting in a single partition, right? Even if I use any of the date.
Yeah, why not? I mean, see,
No,
it is
still I'm scanning only single partition, right? Before cluster also as well as after cluster
okay.
also.
Look at
I'm
this.
using single partition.
Yeah, look at this query. Select name country from T1 where type equal to 2 and date equal to 11/2, right? Now, in this original micro partition, this before clustering, how many micro partitions do you have to scan?
No, my question is, I had like only 10 rows. My 10 rows didn't cross my total memory of 500 MB. So in that case, let us assume only single partition is created.
Yeah.
All the 10 rows sitting in the single partition, which is micro partition 1.
Yeah.
So the 10 rows had a different date like 11 2, 11, 3, 11, 4, 11, 5.
Okay, for 10 rows, you will not create clustering. You will leave it to Snowflake because there is some points you need to understand when you want to recluster. Okay, so
Okay.
when it says, we are anyway going to come here. Table has to be large enough, multi-TB range to consist of sufficiently large number of micropartitions, and columns defined in clustering key should be sufficiently filtering subset of the micropartitions. So for in the range of TB only, you will consider creating a clustering key. Otherwise, you will not. You will leave it to Snowflake.
Okay. Okay. Okay.
Okay. For 10 rows, you will not basically do this.
Got it. Got it.
Okay. See again, even if you go and see the Snowflake documentation, right? They have used this same this diagram, but they have mentioned also that this is just for example. I mean, think from a bigger point of view, like on a larger data set, right? This is just to clarify the concepts of how micropartitions work behind the scenes, how they get arranged when before reclustering or after clustering. So don't take this like as a very literal example. Okay, this is just for your hypothetical, clearing your concepts.
Okay.
Okay,
Hey,
so
the other one, do we have an option to see what are which partition is using my current data, like the row number 1 is sitting in which partition? Do we have an option to view that?
you mean, okay, so you mean this row 1 is sitting in micropartition 1 like that?
Yes. Yes.
No, I have not come across anything like that.
So we are
No.
not sure how many partition that particular table has.
No,
And
no.
where my data
How many partitions and all you can get to know, like how many total partitions are there on the table, that all you will get to know. So I will tell you like how to see that.
Okay. Okay.
Okay. That all you will get to know, but which row belongs to which one, I am not sure. I have not seen that actually.
Okay. Okay. Fine.
Okay, so let's go back to clustering. So you understood what clustering is, right?
Yes.
Based on the column that you create your micropartition, that becomes your clustering key, and that could be one or more than one column. So in this example, what we saw was we did a clustering on date and time. Okay, and here also that's same now. Now imagine what we did was we created one table, we inserted 12 rows, we did not do any clustering, and it created clusters. I mean, it created micropartition as per the order, right? Now what we'll do is, and this is how the micropartition looks. And again, this is a hypothetical, okay? Consider this is a very big data. So now what we do is we will cluster it. We will pass our own clustering key, and we'll say that you need to cluster by what? C1 and C2, okay? Let's say we want to cluster by C1 and C2. And I'll done it like this. And if I go and see it like this, now I can see the cluster by key here. It was blank earlier, right? Now it says you can cluster by C1 and C2. And now again, when we say cluster, Snowflake doesn't immediately go and change the micropartitions behind the scenes. It uses its own algorithms, whether this data needs micropartition at all. Although we have said, okay, do this, it will not do unless it feels or unless it has an algorithm running behind which says, yes, we need to do the clustering based on this, whatever they've given. Otherwise, they will not create. Okay. So don't think that once I fire this, it will start creating it, because the data is too less, right? So it has its own intelligent system to find out. So anyway, so let's consider that it has done it now. And based on C1 and C2, we are going to micropartition. So see, now the order has changed after reclustering, the order has changed. So now in micropartition 1, we have 1, 1, 1, 2, 2, 3, and 2, 4. Okay. Earlier, what did we have? We had 1, 3, 5, 6. So the minimum range was 1 for C1, and max was for C1 was 6. and for C2 was 1 and 12, correct? Earlier, before reclustering. But after clustering, see, the min has become 1 and max is just 2. And here 1, its max is 1 for C2 and is just 4. Okay. This is how the micropartition looks after clustering, reclustering. See, the columns get stored together. And let's now compare both the tables. What are the main? Let's just stick to micropartition 1 and their columns. C1, the maximum and minimum, the minimum and maximum is 1 to 6 before clustering. It's 1 to 2 here. For C2, 1 to 12. And for C2, it's 1 to 4 after reclustering. Okay. Now, suppose we fire a query now. Suppose we fire this query. Where we are going to select C1, C2, and we are going to say where C1 is having values in 2, 5, and 9, and C2 is between 3 and 6. Okay. So what would have happened before clustering, reclustering? So what is it saying? C1 should be in 2, 5, and 9. So one is it having 2, 5, and 9? Yes, 2 and 5 are here. So yes. So let's just look at column 1 as of now. For micropartition 2, what are the maximum and minimum? It is 1 to 6. Okay, this also is required to be scanned. Then micropartition 3 for C1 has 2 to 5. Okay, 2, 5, 9 are there. So this also needs to be scanned. The last partition, micropartition 3. So this is from 3 to 10. So 2, 5, 9. Again, this has 5 and 9. So this also needs to be scanned. So total partitions are micro 3. 3, and total number of partitions that I need to scan for this particular query are all the 3, correct? MP1, MP2, MP3, because it stored it as per the order. So it is going to scan all the micro partitions to get the values. Now, after reclustering, see what happened. So C1 is again what? 259. So 259, 1 to 2, yes, this requires 1 to 4, 2, 5, 9. Yes, this also requires 3 to 4. This doesn't require 5 to 8. Yes, 2, 5, 9. It requires 5 to 6. Also, it requires, and 9 to 12. C2 it doesn't require. Okay, because C2 is also there. So 3 and 6. This one is not required here. This one is not required. So overall, it just has to scan micropartition 1. So after reclustering, before reclustering, it had to scan all the micropartitions. But after reclustering, because we arranged data as in the sorted way of C1 and C2, it just had to scan just one, MP1. And how did it find out which micropartition we want to scan? From the metadata in the header of the micropartitions, which stores the range of values, the distinct values, min, max, row count, etc. So based on that, it found out, okay, do I need to go and check further in this micropartition or not? So it got the answer as yes, yes, no, no, yes, yes, wherever it did not match. So after reclustering, just one micropartition it had to scan. And before reclustering, as you can see, it had to scan all the 3. So this is the advantage of, clustering the table as per your requirement. Did you understand this example?
Yeah.
Yes, sir.
Okay. Okay, fine. So let's, we have understood what clustering is, what clustering key is, and how to give the clustering. So there are 2 ways, as I said. If you are well aware that your table is going to grow big, you can always give the clustering key along with creating table itself. Just by cluster by is the clause, cluster by and the column names that you want to use for clustering. Else, if you have over the time realized that your table needs reclustering, you can go and alter it, same clause, cluster by, and you can give the column names. That's it. Now we know what clustering is. We know what micro-partitioning is. Okay, what is the default way of loading data, and how Snowflake loads data when you give a customized clustering key on the table. That also we know now. Let's try to understand what clustering depth is. Okay. Guys, can we take a 5 minutes break and then continue?
Yeah, sure.
Okay, guys, thank you. I'll be back in 5 minutes. Hey guys, I'm back. Is everybody there?
Yeah, Abdul.
Yes, Abdul.
Okay, thank you. Let's continue. So yeah, so let's look at what clustering depth is. So I'll just read this out and then I'll explain. So the clustering depth for a populated table measures the average depth of the overlapping micropartitions for a specified columns in a table. The smaller the average depth, the better clustered the table is with regards to the specified columns. Clustering depth can be used for a variety of purposes, monitoring the clustering health of a large table, particularly over time as DML is performed on the table, determining whether a large table would benefit from explicitly defining a clustering key. Okay, the clustering depth of a table is not an absolute or precise measure of whether a table is well clustered. Ultimately, query performance is the best indicator of how well clustered a table is. Okay, see guys, I'll explain you with this example. Here, this is again taken from Snowflake documentation. this is an example, okay, where it says there are 5 micropartitions. Okay, and it has got a range of values from A to Z, A, B, C, D, E, F, G to Z. And this arrow that's going down here, it cuts the overlapping values. That means the common values it has in across the partitions. So we just saw what overlapping values are. You have those values ranging into different micropartitions, and you have some other values also in those micropartitions. Correct? So here, in the first case here, all the micropartitions have some common values ranging in them. So overlapping micropartitions are 5, right? And the depth of overlapping is also 5. That overlapping depth is nothing but the average overlapping micropartitions. See, the clustering depth for the clustering depth for a table measures the average depth of the overlapping micropartitions for specified columns in a table. So depending on how many micropartitions are overlapping, the depth is also decided. So here 5 micropartitions are overlapping and they have different values also. That is why overlapping depth is 5. Let's go to the other example below it. So you have 5 micropartitions, but in this case only the range from K to Z have some overlapping data in the 3 micropartitions. So how many overlapping micropartitions you have? 3. And the depth is also 3. Okay. Here, the next example, you have K to N, you have L to S and Q to Z. So L to S and Q to Z have overlapping values, plus they have some other values also, correct? But this KLMN, this KLN, it also has this L to LMN, right? LM, it has L and M in K to N range, but it doesn't have anything up after that, like LMN. It doesn't have OPQRS like that. It doesn't have anything, separate values as compared to this micropartition. Correct? So that is why it is overlapping, but its depth will not be considered. Only the depth of these 2 micropartitions will be considered because they have overlapping values also and separate values also.
Abdul, we have K as well, right there.
Where?
Yeah, the range starts between K, L, M, N, correct?
Yeah.
So L, M, N is overriding with other partition. In addition to that L, M, N, we have K as well, right? The bottom one. Yeah.
K, yeah. So KLMN is there.
Yes,
Okay.
only L, M, N is overlapping with the other partition. So in addition to L, M, N, I have K as well. So here the overlap depth shouldn't be 3.
No. See, look at this. It has top till N, right? it has stopped. It is the what do you call, the extreme end of the micropartition always. See, if you have this element LMN OPQRS, okay, this is QRS, but after this there are more other values here. So this is MLNOPQ, and it is starting only with Q. Had this started with K also, suppose this other micropartition, suppose it had K also here, so then it would have been proper overlapping. I mean, it would have been considered as for the depth also, right? For example, here, let's look at this example here, overlapping. You have 11 by 2 in 1 also, in 2 also, in 3 also, right? But the overlapping depth would be only 2 here. Because whatever data is here purely, it is here also, but there are some other values at the end of the micropartitions. There are other values also here. So that is how you have to consider it. If now we go back to that also, let's see that this, let's see this, the upper one, K2Z. The starting of the range of values is also there in all the 3 partitions, and the end of it is also there. Okay, but here it's not like that, right? So that is why it is, it will not be considered for as the depth here. I know it's a little confusing, but you just need to check for at the end of the partition, and then you will be able to understand.
Yeah, I was checking only for the values. I'm not sure that I should check only at the end of the partition. That's the reason I added K. Yeah, now it's clear.
KLM. Yeah, no, I understand. Even I used to wonder why this is, when you have 3 micropartitions that are overlapping, then why the depth is 2. But if you look at this data here, right? Here, here this is also overlapping only, right? Because it has got 11 by 2 here also, 11 by 2 here also, and 11 by 2 here also, right? But this whatever data is here purely, it is not having anything else. That is why that will not be considered as a part of depth, average depth.
Okay, so even if I had 11.1 in my first micropartition one, still that will not be considered as overlap data, correct?
11.1 here.
Yes.
Yeah, it would not. Yes.
So if I had 11.3, then that will be overlap data.
Yes, yes, correct. Yes, 100%. If 11.3 is here, it will be considered as the average depth will be 3.
Yeah, I was checking only for the values. So now I understood that I should check only for the end of the partition. Okay, fine.
Yeah, yeah. And if you look at the last one, there is no overlap with any partition here. All have their own individual set of data which is not having overlaps with any other partition. So overlapping is 0, and whenever overlapping is 0, the depth is called as 1. Okay, so this is the most ideal scenario, and where we just saw that smaller the average depth, better cluster the table is. Okay, so smaller the average depth, that is better clustered, because obviously if the average depth is more, you basically, if you want to, in this case, first case, you want to say scan where you have a where condition which says column equal to value equal to A. So basically here in this case, you will have to scan all the micropartitions, right? Because A value is cutting across all the micropartitions. So obviously you have to scan all of them. But in this case, if you want A, you just have to scan 1. In this also 1, in this also 1. So basically the lesser the average depth or overlap depth, it is better clustered. It is considered better clustered, and it is better for performance tuning. Although they say it is not an absolute measure. Okay, if you have a table where performance is good, you're getting your rows in a quick time, you don't have to worry. Okay, over the time you can go and check. Suppose it starts to your performance degrades over the time, maybe a lot of DMLs kept happening, and the data got skewed, or it started to get loaded in a unsorted manner, and the micro partitions are not no more you can say optimal. In that case, you can go and check the average depth and then decide what to do. Okay, and then again, this is we'll see what are the factors that you should do clustering on. Okay, so these are two views: system dollar clustering depth and system dollar clustering information, which gives you the information on the clustering key, the partitions, the what do you call clustering depth, etc. Okay, so we will look at that also. I will fire some queries there and I will show you like what all to see there. Before that, let me show you one more use case here. Uh, yeah, see guys, this suppose you have micropartition 1, 2, and 3, and 4. You have all these values here, right? A, B, C, and all that. So see, micropartition for value A, micropartition is in 1. The micropartition value is just 1. For B, it is 1 and 2. For C, it is 2 and 3. For X, it is 3 and that's it. And Y and Z also 4, 4. So my total micropartition count is 1, 2 for B and C, and 1, 1 for all the rest of them. So, and let's see what are the overlapping micropartitions here. So for micropartition 1, you have what all overlapping? It is overlapping with 2. So just one micropartition it is overlapping. For 2, it is overlapping with 1 also, and it is overlapping with 3 also, because B is here and C is here, right? So 2 is overlapping with 1 and 3. So you have 2 overlapping micropartitions. If for 3, if you look at 3, micropartition 3, it is overlapping with 2 because C is here and C is here, right? So it is overlapping with 2 and just 1 micropartition. 4 is overlapping with nothing, right? So 0 is the micropartition overlap. Number of micropartitions overlapping is 0. So overall average here becomes 1. Okay. So it is since the average depth is 1, it is a better what do you call cluster table. See this. A to B, B, this is an overlap. This is an overlap, and there is no overlap here. Correct? That is, I will share all these documents with you also. And here they are just saying what is there an overlap with A. If you have value A in the micropartition, is there an overlap with any other partition for value A? There is no overlap. It is just residing in micropartition 1. For B, if you want to scan B, you will have overlaps 1 and 2. For C, 2 and 3. For X, Y, Z, there is no overlaps. They are in single partition only, right? So all this, this is one use case. You can just try to understand the concept of overlap. What is an overlap, and what micropartitions are getting overlapped based on the values. So based on the values, you have to understand what all micropartitions are there which are getting overlapped. Okay. Now, coming to a little bigger demo actually. Okay, we'll do a demo. It will take maybe more 30 minutes. Let's quickly do that. I hope you guys are not tired, because this is one concept in Snowflake which requires a lot of maybe understanding and attention actually. So Vinod has done the level up series, I guess. So Vinod, did you come across this micropartitioning there?
No, I did not go with the micropartition. I stopped at monitoring and caching.
Okay. Maybe today, so there must be this micropartitioning series, is it there?
I did not find it, but I don't remember seeing it. That I'll
Okay.
check. Because...
Okay. So just have a look. If you find it there, then try to attempt it today.
Sure.
And what about you, Arumoto? Did you get chance to do those level up series?
Not yet, Abdul. I'll try to finish it today.
No, take your time. It's quite a big one. So, I mean, do as per your, you know, as per your schedule. But yes, try to do that.
Sure.
DemoDB. So under DemoDB for my previous classes, right, I had created those tables actually. So let me drop it for you guys. Actually, I load this data prior to the class starts, but sometimes some students don't understand. So I thought, okay, I will just load it in front of you guys only, taking some suggestions from the previous class. Okay. So see, what I'm doing is in my demo DB, okay, I'm going to create a customer cluster table. Okay. Or yeah, okay. First create one. Let's create one non-cluster table. Means you don't have any clustering key. Okay, it is you're leaving to Snowflake to create partitions as per the data that comes. Right. So let's do this. So what are we doing is, that Snowflake provides us with sample data, right? It provides with this shared data, Snowflake sample data. You guys know about this. I had explained to you, right? What is the purpose of this? It has got these schemas.
Yeah, for unit testing, we have multiples of same data, right?
Correct. Same, the size increases. One has the least 10 by 10 factor and so on. And this is for your performance testing most of the time. Okay. You can use it for that. So what I'm going to do is in my demo table, demo DB, I am creating this customer table and I'm taking it from the 100 SF100 schema as it is. Okay. Forget this, what this transient means. Okay. We have a separate topic for this. Forget this as of now. So I'm creating one table in demo DB and this has got how much data? 700. 1 GB. That's about it. Let me increase the size, guys, of the warehouse so it gets completed a little quickly. Figure it is X small, right? I'll make it large. Finish. I made it large because for 1 GB data it might take time, so it was excess. And after that, I told you that we have this to check the clustering information. We have this context function system dollar clustering information. We'll see that what it is. Okay, see how fast it got created, right? Because I used a large warehouse. Let me go and resize it. For other queries, again, when we want, we'll go and resize, make it extra small again. What happened?
You're creating new one, right?
Oh, sorry, I need to config. That's why I was wondering why that name field is not coming. Okay. So now we have this table created in DemoDB. Let's go there. So we have demo DB. This is demo DB. We created this table called customer no cluster, and it has got around 1.5 GB data. No, not 1.5, 722 MB data. Customer no cluster, right? So if you try to see a few data set, this is the data that we have in the table. And if you want to see the clustering information, clustering key, we can do like this also. And okay, so that is not the name of my table. This is the name, okay. And see, it says we don't have any cluster by, and the rows are this 757 MB and so on. So if you want to see more information of clustering, so there is a function called context function called system dollar clustering information. The arguments that you need to pass are the table name, and in case you don't have any clustering key that you have defined on the table, you can try to pass some column and see what will be the future micro partitioning if we cluster by this key. It will give you how good will your clustering be if you use this to cluster it, this column to cluster it, or a combination of columns to cluster it. Okay, so this is going to give you a kind of preview. Okay, it is not necessary it will work properly, but it will give you some idea. Okay, so right now I don't have any clustering key given to this table here. This is where I created it, right? I did not mention any cluster key here. So if I try to say, so I have one column called market segment. Okay, so if I try to look what all market segment I have, suppose I'll go and check in this table to select. I'll do a distinct from this. Okay, so I have these distinct market segments in that column: machinery, furniture, household, automobile, etc. And now what I'll say is, okay, let me have this as my cluster key. So let me see how would it look before I do a recluster on it. Okay, so let's see what all information do we get when we fire the section, when we fire this command here. So we get output of as a JSON object. Okay, your key value pair, that is your JSON object. So it shows you cluster by keys. What will be the cluster by keys? So right now it will cluster it by market segment. It is not clustered it. It will tell you what it will cluster it because we have passed that particular column. Total how many partitions would be there if we cluster? It would be 72. Constant partitions would be 0. Constant means the partitions which will not have any overlap. Okay, the overlaps would be 71. That means 71 partitions would be overlapping, and the average depth would be 72. And this is the micro partitions that would be created. The histogram is this. So there will be 72 micro partitions that will get created. And so I mean these micro partitions will be created 1, 2, 3, 4, 5, 6 and all that. And this particular partition will have a average depth of 72. And rest all will have zero depth. So which is good, right? Only the last one has little more depth. So total number of partitions would be 72, and this would be a histogram depth, correct? Now what I'll do is I'll fire a query on this table and I'll try to get some columns. Okay. Not all columns. Let me just see what all columns will I get. I'll try to get cluster key, customer key and customer name and an account balance. Okay, now let's see the other one also. Just before going to that, sorry, let's see what if I want to cluster the same table by market segment as well as cluster customer key. So let's see what happens. So see, it will give you notes also here. See what it says. Clustering key columns contain high cardinality key cluster, which is cluster key, which might result in expensive reclustering. Please refer to this document for more guidance. So clustering customer key in any table would be unique, right? So for that 15 million rows, whatever it was, each row will have a unique cluster key, customer key. So imagine if you want to partition by that, so that will divide so many partitions, right? And it will create so many partitions and you will have to prune and scan through the metadata of so many partitions. So if you have a very high cardinality column, it is not advised to create a cluster key on that. And Snowflake intelligently has provided a note also here. In the previous one where we checked for market segment only, it did not give any note. So it is quite okay there, right? So in this case also, it is not giving a proper picture of total partition count here. But although it has given you the note that it is not advised or it might result in expensive reclustering. Okay. So let's, now we will not recluster, we'll simply fire a query and see, try to fetch certain columns from here and see what happens. And this here is just a futuristic representation, guys. Okay. It is not necessary that it will be 100% like that only. First key, C underscore name, C underscore A, CC feedback from this my segment is say household. Okay. So let me go to the profile. So I have fetched 3 billion rows. Okay. So how many rows it got? 3 million rows. I go to profile here. So see, it scanned. It has got total partitions as 72, and it scanned all the 72. Correct? The table scan was all the 72. Now, what we'll do is we'll create a cluster table from the market segment here, and on that we will we'll see how whether there is any improvement or not. Okay, we are going to create a same table only, but this time we are going to pass a clustering key this time. So
rather creating the same table again, we can alter and create a cluster alone, right?
Yeah, we can do that also, but I want to compare and show it to you.
Both should be doing the same process, right? Even if I create a replace or just altering, both should give me the same thing, right? No?
Yeah, but Snowflake does not recluster it immediately. So we don't know how much time, we will have to wait for it.
Okay.
Okay. So same column, same everything. Just the name of the table is customers clustered. And now I'm going to cluster by market segment. So I'll create a table here. Sorry, I need to this one. clustered here. Now let me get all these values here. These commands here. We already know this. Okay, so here so it's going to cluster. It has already the cluster information here. It's going to cluster by market segment when I insert the rows. Okay, and now suppose if I fire this on the customer clustered. In this case, if suppose I don't give the second parameter, okay, in this case, it will return me the cluster, the column, the values for the clustering information based on the cluster column I have created. Okay, if I don't pass the second argument. So for this, it takes the clustering key I defined on the table as the default if I don't pass the second argument. But if I come here where I have not, if I have not clustered the table as per my customization, and if I don't pass anything here, so it will give me invalid clustering keys or table cluster is not clustered. It will give me this error. Okay, so not giving the second argument only works when you have created the table using a clustering key. Okay, and rest is the same. You can pass some other value and see what will be the result. That is all fine. That remains the same. Okay, now let me insert the rows here again. I'll go and change this size again just for that purpose. Large. And I'll insert all the customer rows here. Okay, good. Now let me go back and resize it. Finish. And we will fire that query again now here and see. Okay, so we have the data. Okay, see, this time it scanned more. Even though we have clustered it, right? We have clustered it properly. It scanned more. Earlier it was 81 bytes, 81 MB something. And this time even it created more partitions. Let's look for the other distinct ones, other what do you call marketing segments, if it makes any difference there. For maybe what automobiles. Okay, no difference here. Let's look at machine learning. No difference here. Okay, so I'll tell you guys why there's not much difference here. In fact, it has what do you call it? It created extra partitions because see guys, let's go and see the tips here. Okay. See, clustering keys are not intended for all the tables. Size of the table and query performance should dictate whether to define clustering key or not. Table has to be large enough to consist of sufficiently large number of micropartitions, and columns in clustering key should be sufficiently filtering subset of micropartitions. The cardinality of the columns should be medium and should contain good enough number of distinct values. Example, gender and customer ID columns are bad examples of clustering key columns. See guys, out of the 15 million rows, we basically did what? We created it on the market segment, right? And see the number of distinct values. It has just 5 distinct values. Okay, so if we want to calculate the cardinality, we can always apply this formula here. Okay, this one. So you have total number of, so you have distinct number of values divided by the total number of rows. See, it's not good, right? It's not that good. So that is why, since the cardinality is very low, in this case it is very low. So what it says here, it should not be either high or very low, it should be medium. And examples of gender and customer ID are some examples. So gender has a very low cardinality, like it would be either male, female, transgender, or maybe one more, I don't know. Customer ID would be unique for each row. So if you have 15 million rows, you will have 15 million distinct customer IDs. So that is not a good ideal way of having a clustering key done. So this is a very bad example, right? So in this case, doing this clustering or market segment is not feasible. In fact, it created more partitions and it disturbed the whole thing also. So let's try to maybe cluster it by, okay, now what we will do is, we all know, okay, let's come back to our non-cluster table. We all know that when you don't assign a clustering key on the table, Snowflake will load data as per its own, as per the data is loaded, correct? So what we will do is, we will order by, when we are loading the data, we will order by market segment, okay, and then see what happens. Okay. Here, what we'll do is, yeah, we will create one more table called as order by, and while inserting, we will do an order by market segment. So all the machinery will go first, all the automobiles will go second, and so on. Whatever is the order by, that we will do for our non-clustered table only. But that would be ordered by. So let's create this table again. Let's call it order by. And here we will order by the market segment. So because we are not passing any clustering key here, and Snowflake will create partitions as per the data that gets loaded. So we have ordered by ourselves this time. Okay, great. So we have created the order by one, right? Let's go to warehouses again. Okay, now we'll try to fire that query. There's no clustering key on this. Okay. See, 30 million, but it had to just scan 30 MB this time. If you go to profile, see, out of 108 partitions, it just had to scan 25. Because initially only I ordered by, for example, in this case also, let's go to our case here. This one. Had I, while loading the data, if I would have mentioned saying that, okay, order by the date column. So all the 11 by 2 would have come first, 11 by 3 would come next, 11 by 4 and 5 would come next, so on. Similarly, for this, I said, okay, while loading, you order by the market segment where I want, automobile first, machinery second, and so on, whatever is the order by, So that is why my micro partitions were, properly clustered, and it is giving me just 25 partitions to scan from 108 partitions. See, and only 30 MB of data I had to scan. That's it. So what basically here, what it did was when we clustered by okay, let's try to alter it by reclustering. I think we need to, when that cluster table that we did, right? I think we need to recluster it exclusively. Let's go there and recluster it maybe, and see if any impact is there. Where was I? Order by. This is non-cluster, and this is clustered. Okay. Table. Oh, I'm sorry. This is already clustered. Sorry. Okay. We could, we could have, so we have this non-cluster here, right? So this one we can recluster if you want, after like what Arumugam was saying. So let's try that. Right. So see, it is reclustering it. And there's one more column here, guys. There's one more function here, clustering depth. Here you can just simply go and see the clustering depth of your your tables, and then you can pass some columns and all. If you want to pass columns, you can find the clustering depth, like what all micro partitions, how many micro partitions, average micro partitions you have as your depth. You can pass values also. For certain value also you can check, and for certain columns also you can check, and you have to pass the table first. So so what we discussed about depth and all, right? Overlapping depth and micro partition, that is only what it is going to give you back, this particular clustering depth. But all this information you anyway get from clustering information, the whole information. Okay, let me recluster that. See, it has started the reclustering here now. Earlier it was off, right? Because there was no recluster we had provided. So it will do the clustering, automatic clustering. See, after reclustering, it has created as 50 partitions and scan only 11. See, no cluster. Earlier there was no clustering on this. Later on, I created the cluster and I fired a recluster on it, and it scanned only 33 MB records and it scanned 11 partitions and it created 50 partitions. So I got an advantage of this. But in this case here, I'm not sure why this one did not work. It should have also worked here properly. Okay. Anyway, I'll look into this later. But yes, after reclustering, you can see the difference, right? Earlier there was around 70, 72 partitions and it was scanning all of them. But later on, when I reclustered it, it just scanned 11 and it created 50 partitions. So it had the, so it did not, I mean, that cardinality was not an issue in this case as such, which I had told you earlier. It did not become an issue. I was thinking that that might be the problem, but I don't know why it did not take this cluster by here. I will go and check later on and tell you next week, like what is the problem here exactly, because it should have created a cluster. I mean, it should have created the micro partitions here. Because we have already, okay, this will take from the cache. Okay, so even though I mentioned, that it should create the cluster by, it did not create 50 partitions. So as far as partitioning or reclustering is concerned, right? What happens is Snowflake doesn't immediately do it. Okay, it takes it will first go and analyze it later on whether it needs to be done or not. So maybe it will do it later, or I will need to see by tomorrow if it has done or not. Okay, so yeah, I think today we can stop here. Is it okay?
Yes.
Okay. Any doubts today? For today, we can take questions if you want.
Abdul, can you go to that micro partitioning screenshot? I mean the PPT.
Yeah, this one.
Yeah, scroll up before clustering, the initial one.
This one.
Yes. Okay. See, here the metadata will have the range as well as the distinct value, correct? Based on that only, whenever I fire my query, it will go to the respective micropartition, correct?
Yeah, it will check from the header, MicroPartition metadata.
If my column has 100 distinct value, means still it will display the 100 distinct value.
Yeah. Whatever distinct values you have in this micropartition. So I see, look at, I have given you this example here. If you look at this here, okay. So in this micropartition 1, it has got column 1 as 1, 3, 5, 6. Okay. So minimum is 1 and max is 6. And the distinct values will be 1, 3, 5, 6, all will be distinct values. Yeah. But if you recluster it later on, say based on column 1 and 2, this one here. So micropartition 1 has minimum as 1, max as 2 for C1, and only 1 and 2 are distinct values here. For C2, minimum is 1, max is 4, and 1, 2, 3, 4 are distinct values here, like that. So if
Okay.
so, I have arranged it here like this. That is why I don't have many distinct values here compared to the one before clustering. This one.
Okay. Okay. If we are doing clustering, yes, then it makes sense. If not, then if I have a huge volume of records, then holding a distinct value means that's what my question is. Where it will store that information will be stored in the metadata?
Yeah. So this header, there will be a header for MicroPartition. I think I don't have that slide here, but there'll be a header in the MicroPartition. See this here, this one here, file header, which will have minimum. So this is one MicroPartition, suppose, and it will have a header here where it will say minimum value, maximum value, and number of distinct values for each column.
It will have number of distinct value, or it will hold the distinct values.
Number of distinct values.
Okay. So it will not hold the values, only the total number of distinct values only, right?
Yeah. But see, I'll tell you one thing. This is not in our control, and you actually don't have to worry about this, because every time you are going to load data, right, that all this metadata management will be done by Snowflake. We will anyway have no control on this.
Okay, fine.
But what maximum you can do to improve your query is analyze if you have any good clustering key that you can apply on the table to, for example, how we did in this case here, we reclustered the table on market segment. Later on, first we created a normal table without any clustering, which was having 72 partitions. Later on, we reclustered it somewhere here, right? Yeah, we reclustered it here, and we said by market segment recluster it. So when we did that, then after that it deleted all the old partitions, created new partitions based on this. So that is why now we have 50 partitions and only 11 that were scanned out of it. Yeah. So this you have to analyze basically. What can be my clustering key based on the data, kind of data set you have. Okay. So I was here in this case. I created a clustering key while creating it a table itself. Okay, but it did not do what was expected. So there might be some issue. Whether it is, as I said, it doesn't immediately recluster, or I don't know why. I'll have to check why it did not. Here I had written it. By during the definition only, I said cluster by market segment, but it did not, follow it. So if I do it, if I fire this query again, you see it has created 78 MicroPartitions. Even though I said cluster by market segment. Okay. In the other case, I did alter by it, did it immediately, but here it did not. So I'm not sure why it did not do it. I need to go and check it later on. Automatic reclustering is also on. I need to check if there is any command to force. I will have a look at that, guys, and let you know. Okay. But the thing I told you that because of the cardinality, that could be an issue, but that doesn't seem to be an issue. Okay, so My bad there. Don't take that into consideration, because here we proved that market segment was a good choice to cluster when we did the reclustering, right? So
Mhm.
so just ignore that. Because I was thinking because of cardinality that might be an issue, but this seems to be something else. I don't know exactly what, why it did not take the clustering even after defining on it. Maybe I'll just have a look at it and let you know if I get something. Okay, guys. So any more doubts? We can then conclude for today.
Yeah, I'm good, Abdul.
Okay. Okay. Vinod, you're okay?
Yeah, good. Yeah.
Okay. Fine. Thank you, guys. And I'll see you next week. Thanks a lot. Take care.
Thank you.